So in my talk today, I'd like to start with a kind of brief introductory overview of some of the main principles of quantum computing and algorithms for people who might not be totally familiar with the subject, and then go on to mention some more specific quantum algorithms that are likely to be candidates for significant applications in healthcare and medical sciences. So go to the very beginning then. Quantum computing, the subject, begins with a realization that there's a necessary and rather profound connection between computation and physics, which was emphasized by early pioneers like Rolf Landauer and David Deutsch, as we kind of see here. And this becomes apparent if we ask, what is information and computation fundamentally? And, thinking about information, it's usually represented using bits, and bits in turn are usually written as Boolean values, 0 and 1, which in fact are kind of mathematical abstract concepts. But, that can't be what information is. It's not abstract. When we get information, we get something that we didn't have before, as it were. And it's not just a mathematical concept. And it was emphasized, especially by Landauer, that there's no information without representation. And by that he meant that when we get information, we always get a state of some physical system, one of two possible states, which we label as 0 and 1, and then we carry out a physical measurement to acquire the information of what it is. So that provides a fundamental connection between the physics and the information. And then information processing or computation is updating the information. So that has to be a physical evolution of the information carrying physical system. And we see immediately that the possibilities and limitations of everything to do with information and communication and computation and security even must depend on the laws of physics, and they cannot be determined by mathematics or just pure thought alone. So that realization has enormous consequences because classical physics and quantum physics differ greatly in their perspectives when viewed from this perspective. So to begin with, if we think about physical states representing the information, so here we have our two classical states, which we just call 0 and 1. In the quantum case, we have two quantum states which should be distinguishable, and we put these asymmetrical brackets that just symbolizes their quantum states. And in quantum mechanics, they're always vectors of length 1 as well. So if you have states, you can consider superpositions of them as well. They must exist. And we get these superpositions, which are physical states in which 0 and 1 are both present simultaneously in a peculiar sense, which is not possible classically. And we'll say more about that in a moment. But then it becomes more interesting when we go to many bits and qubits. So classically we have n-bit strings. There's 2 to the n of them, as you obviously know. And similarly for n-qubit states, you have these quantum states, 2 to the n of them, labeled by the bit strings. But now we have general superpositions. So this may seem all rather, natural and pedestrian, but in fact already something spectacularly amazing has happened here. And this is the phenomenon of entanglement, which we see if we consider the number of parameters needed to describe the states in the two cases. So an n-bit state, the number of parameters grows linearly with n, because an n-bit state is just n bits next to each other, and you need a certain constant number for the description of parameters for a single bit, and then you just have n times that many. But in the quantum case, because of the superpositions, you can have exponentially many things here, and to describe a quantum state of n qubits, a physical system of the same comparable size to the classical case, you need exponentially more parameters in the description. So in a sense, quantum mechanics allows us to code exponentially more information in a system of a similar size. And this is a very remarkable thing. So, and that's used a lot in quantum computing. So moving on to physical evolution and computation eventually, in quantum theory, physical evolutions are always linear maps, like matrices multiplying the state vectors. So if you update a system by a quantum evolution in a superposition like this, all the different superposition components will all get updated separately, and you get this kind of parallel, exponential parallel richness in the computing power you can make out of this. So to be slightly more specific about computation, we imagine a very common model of computation, the gate array model. Classically, we can think of a computation as an array or circuit of AND, OR, and NOT gates acting on a string of qubits, which represents the information you're updating. Quantumly, you do a similar thing. You have an array of quantum gates, which are just linear transformations, each acting on one or two qubits, just like the AND, OR, and NOT gates of a multi-qubit state, and you evolve the state that way. So a fundamental example to sort of put all this together is, suppose you have a means, say a program or a black box or oracle for computing some Boolean function from n bits to 1 bit. There are 2 to the n values, fx's, for x being n bits for this function. And classically, we input the x value, and we have an output register which initially is set to 0. And then it computes the value and writes the answer here. So quantumly, we can do the same thing and we get that. But now, in the quantum case, because of entanglement and the superposition behavior that I've been describing, we could easily, in fact, prepare the X register here, the input register, in an equal superposition of all 2 to the n values, and run the computation, this wiggly arrow, the program or the oracle, just once, and produce a state which contains in its state description all exponentially many function values for the price of one computation. Now, that's a very remarkable thing, and you can't get anything like that classically, any representation of all the function values without very exponentially many computations. So, that seems all a bit too good to be true. Quantum mechanics is sort of handing us for free, just handing us this exponential parallel computing power for nothing at all, basically. But there's a catch. It's not as good as it seems, because you need to also be able to access the information and read it out. So there's another aspect of quantum mechanics, quantum measurement theory, which provides the classical output results from a quantum computation or a quantum state that you get at the end. And I don't want to go into the details of all this, but the basic quantum measurement rule has the following very awkward feature. If you're given a multi-qubit state of, say, n qubits, so it's got kind of exponentially many bits of information in it, if you like, to prescribe the state, then any physical measurement you can do on it will, to read out some information about the identity of the state, can reveal only a very small amount of all that information, in fact, only about n bits of the exponentially much about its identity. And furthermore, after the measurement, the state collapses, or it's irrevocably destroyed and collapsed to be consistent with whatever result came out probabilistically in this measurement. And all the other information is lost. So it's as though nature is doing a massive amount of computing work to get all these values in superposition, but then deliberately preventing us from reading out all that information. So, and here's an example of this. If we, well, more precisely to start with, if you measure the bit value of a superposition state like this, the basic rule is that you see some one of the n-bit values x with probability given by the square of the coefficient that it came within the superposition here. And then after the measurement, the state is no longer that, but it collapses to just the x that you've seen in the measurement. So for example, if you read the bit string for these n+1 bits here in this superposition state, then you'll see some one of the fx values chosen uniformly at random and all the others are gone. So you might think, well, that's pointless. I mean, we could have done that classically just by picking a random x and asking that. So, so this appears severely restrictive and it kind of annuls the benefit I've been trying to promote, you know, before we started talking about measurements. But all is not lost here. What you can do is instead of reading that state straight away, this output state containing the 2 to the n values, you can apply further quantum further quantum operations to it, further computation to it, to interfere all the different superposition components and still read out a small amount of information which, although small, can be global information about all the values together and still hard to get classically, even though it's small without a lot of evaluations of the function. So you still get a computational benefit. And most of the early quantum algorithms are actually based on just this procedure. So for example, perhaps the first one here I have to advertise is the so-called Deutsch-Jozsa algorithm. And in this situation, the Boolean function is promised to either have all the values the same or exactly half the values, 0 and half 1. And we want to figure out which of those two cases holds. And classically, you can argue that you need order exponentially many evaluations of the function to do that, but quantumly only one. So that's an exponential benefit. And perhaps the most famous quantum algorithm, Shor's algorithm, well, what we do here is we first convert the problem of factorizing an integer into the problem of determining the periodicity of a function. And then we can read out the periodicity from the superposition of all of its values in a way that's exponentially more efficient than you can do classically. And that's a very famous and important algorithm. And then there are still further things. There's Grover's algorithm, or so-called database searching algorithm. And I won't describe what these things are, but I just want to illustrate here that in this case, you only get a quadratic benefit as possible. You know, classically, you need exponentially many evaluations. Quantumly, you need square root of that many, and necessary and sufficient. And then for still further problems like parity and majority, you get no benefit at all. So what's being illustrated here is that there are still situations where you get massive quantum benefits, but you don't get it always. Quantum computing is not a silver bullet that's going to solve all hard problems for you. And it's a kind of a dark art and black magic as to figure out which problems are amenable to quantum advantage and which ones are not going to be. Okay, so that's a very quick look at some basic quantum computing theory. And now I want to just briefly mention a few algorithms, you know, that are going to be more relevant to healthcare. Now here, these things are all kind of mathematical computational tasks, but quantum computers are going to be good also at simulating quantum systems. So there's a so-called digital quantum simulation algorithm. And This will allow you to simulate the dynamics of a quantum system on a quantum computer to generate the evolved state, and then you can do measurements on that to get properties of the evolved state. Now so for example, you can evolve molecules and their interactions in quantum chemistry. You can map the electronic structure of molecules to qubits by standard mathematical techniques like Jordan-Wigner transformation, and the number of qubits will grow linearly with the number of atoms in the molecule, so the state description grows exponentially in its parameters, so it rapidly becomes intractable for classical computation, yet still okay to simulate on a quantum computer. So in quantum mechanics, time evolution is determined by so-called Hamiltonian operator of the system, and for n qubits, it's a great big matrix of size 2 to the n by 2 to the n. And if it has certain special forms, in particular a local Hamiltonian, it's possible to break down this calculation of this thing here to a sequence of basic quantum gates and then program it on a quantum computer. So this algorithm provides an exponential benefit in many useful, or at least some useful situations. And I won't say any more about that, so we can move on to the next example. This one is to do with systems of linear equations. So this is this celebrated so-called Haro-Hasidim-Lloyd algorithm, HHL. What we have here is we want to compute properties of the solution of a linear system of equations, AX equals B, where A is an n by n matrix and B, the right-hand side, is a column vector. And we're thinking here of the system as being very large, potentially exponentially large, making classical computation not feasible to do. But there's a quantum algorithm which will get you useful things here in certain contexts. So there's a lot of technical requirements here for the algorithm to apply. And I've just listed a couple of the more important ones here. So first of all, there are issues with how the input data, capital A and B, are given to you. So the algorithm will need the right-hand side as a normalized to length 1 as a quantum state vector like this. So it'll be an n qubit state for capital N equals 2 to little n. And there are issues, if the B's are given as a formula or as a database of values, there are complicated issues or possible ones of how to convert that data into a quantum state of this sort. But for some situations, you still can do that. And A should be suitably well behaved. It should be a well-conditioned matrix, not too close to being singular. And the entries should be suitably, efficiently accessible. So for example, it suffices to have something like, given the ij, the row and column, there's a classical method of efficiently obtaining the value that goes in the matrix at that place. So given all those things, and a couple more small things, the HHL algorithm will run and it outputs an n-qubit state which corresponds to the solution, again given to you now as the coefficients of an n-qubit quantum state. Now, I said near the beginning that we can't read the solution out from this. It's sort of all hidden there for us, but we can read out properties of it, which depend on all the exponentially many values. So for example, you can perform measurements on this state, and according to the laws of quantum mechanics, when you perform measurements, you get probabilistic answers, and the average values, the mean values of those measurements are given by these quadratic expressions in the coefficients of the state, like this, where capital M are certain Hermitian matrices corresponding to the measurement. And so these can be estimated by measuring a number of copies of this state produced by the algorithm. And there are examples of this where classically the best known algorithms need polynomial in capital N, the big numbers size time, whereas the HH algorithm runs in logarithmically capital N time, and which is then an exponential advantage again. So, so I've only tried to gloss over the, just the bare bones of this, but it's perhaps significant to point out that there are useful, interesting applications where it does apply, like least squares fitting. There's lots of places in machine learning algorithms where you deal with large systems of linear equations, and finite element methods for discretizing partial differential equations and so on in their numerical solutions. Okay, so that's another potentially very useful algorithm. And finally, I have to mention, at least briefly, as I see my time is running down, what's called variational quantum algorithms, VQAs. These are a topic of very much current research interest, and over the last few years. They're rather interesting. They have a kind of hybrid classical quantum structure. You do both classical and quantum computing alternately in them. And they have good features because of the way the classical breaks down the quantum progress. They have good features for implementation on emerging quantum computers, which are limited in size and perhaps slightly noisy as well. I guess like the IBM one and others. And however, they're widely regarded, these VQAs, as a route to the most promising avenue to near-term demonstrations of quantum advantage in possibly useful situations as well, rather than just demonstrating it in principle. Okay, so these are rather have an interesting structure. So basically they deal with the issue of trying to optimize a cost function or minimize a cost function. And many problems can be reformulated as optimization tasks, even if they aren't one to begin with. And another important ingredient is the so-called ansatz, which is a choice of parameterized quantum circuit. U represents the quantum circuit, and X is a parameter which determines what gates you put in the circuit. The gates depend on this parameter X. And corresponding to X, you have the cost function values C of X. And we have the property that the value of Cx and other properties like its derivatives can be classically efficiently computed from measurements on this circuit, this quantum circuit, run on some fixed input state here. And this is the quantum advantage of these algorithms, because the cost function should also have the property that it can't be classically efficiently computed given X. So in other words, this quantum circuit, this parameterized family of quantum circuit, gives you access to exploring part of the landscape of the cost function that cannot be explored, feasibly classically. And the solution should be the minimum over X of these values. So, and a second important ingredient here is that the ansatz should be trainable. That is, given the values of Cx you get here and its derivatives perhaps, the parameters can be updated to improve the value of Cx by classically efficient means, like, for example, gradient descent, so that you can move X to a better value which will minimize the cost function. And then you keep iterating A and B one after the other and converge, hopefully, to the minimum C star here. So that's basically how these things work. And I haven't got time to explain it, but let me just at least expose you to perhaps the most famous example of such a thing, and I think it was the original one, of which what I've just said is a kind of generalization of the structure, and this is the so-called variational quantum eigensolver. And this is particularly useful in computational chemistry and perhaps biomedical applications, because given a Hamiltonian for, say, a molecule, a key problem is to determine its ground state and its ground state energy. there's quantum ground state and ground state energy. And this can be done by one of these algorithms, these VQE algorithms, and I think it has been even implemented for very simple molecules where you can even simulate the algorithm classically. So I won't describe how that works and just say that this thing exists and it's important and it's well suited to near-term quantum computers. And then just very finally, it also has significant problems. So there's much more further research that needs to be done about these algorithms. It can actually provide heuristic algorithms for everything I've mentioned, which don't look like optimization problems, but can be formulated as such. But there are many problems with heuristics and the performance and proving the performance generally. In particular, how you choose the ansatz and the initialization strategy and how to avoid getting stuck in local minima and barren plateaus where the derivatives are very small and so on. Okay, so this doesn't come and give you a whole lot of stuff for free. There's a lot of work to be done, but the point is it's extremely optimistic and it has been shown to be usefully valuable in at least some situations so far. Okay, so that's a very quick, brief overview of some, as I see it, most significant quantum algorithms as we know them now for applications in the sort of health and biomedical area. And I think, as I've run out of time too, I'll stop there and thank you very much for your attention.